All right, let's talk about the moment, the single paper in 2012 that really lit the fuse on the entire AI explosion we're living through right now. This is the story of AlexNet. So, think about this for a second. At the heart of it all is this one huge question. How do you actually teach a computer, a machine that just thinks in ones and zeros, to truly see the world the way we do? That was the challenge they were up against.
Okay, so to really get why this was such a big deal, we need to rewind the clock a little. We have to understand just how hard this scene problem was. Because honestly, before 2012, computers were pretty much blind to the messiness of the real world.
And here's what I mean by that. For years, sure, computers could see some stuff. But we're talking about really simple, clean things, like recognizing a handwritten number on a white background. That's one thing. But asking a computer to spot a leopard half hidden by leaves with sunlight filtering through the trees, that was a completely different universe of difficulty. And this is where the AlexNet challenge comes into play. You really can think of it as the Olympics of computer vision. This wasn't about 10 digits. This was the big leagues. 1.2 million real, messy, everyday photos. And the job was to classify them into 1,000 different categories. I'm talking everything from leopards to cherries to container ships. It was the ultimate test. And progress was being made, but it was slow. Just tiny incremental improvements, year after year.
So how did this team of researchers plan to tackle it? Well, they weren't aiming for another tiny improvement. No way. They were swinging for the fences. Their big bet was to build something inspired by the most powerful visual processor we know of, the human brain itself.
Now, the idea they were working with, a deep convolutional neural network, or CNN, it wasn't brand new. The theory was great. You build a network that learns in layers, kind of like our visual cortex does. It starts by seeing simple edges and colors, then builds those up into textures and shapes, and finally into whole objects. The problem was, training a network that big on that much data, everyone thought it was basically impossible, a non-starter. It would take months, maybe even years to train.
And this is so important to understand. The final breakthrough wasn't some single magic bullet. It was a combination of brilliant solutions to three distinct, massive problems, roadblocks that had stopped everyone else in their tracks. So let's break them down.
First up, the speed problem. Just the raw, agonizingly slow pace of training. The way traditional artificial neurons worked, they'd sort of get tired. Once their output got high, they'd basically stop learning. For a gigantic model like this one, that was a death sentence. The learning process would just crawl.
Their solution was just beautifully simple. It was a new kind of neuron called a rectified linear unit, or ReLU for short. And you can think of it as a dead simple on-off switch. If the input signal is positive, it lets it through. If it's negative, it just shuts it off. That's it. But that tiny change had a staggering effect. It allowed the network to learn 6 times faster. All of a sudden, that impossible timeline started to look possible.
Okay, problem number 2 was a hard physical limit, a wall. The network they designed had 60 million parameters. In 2012, the absolute best graphics cards you could get your hands on had about 3 gigabytes of memory. The model was just too big. It physically would not fit. It's a classic square peg in a round hole problem.
So what they did was just an incredible feat of engineering. They literally split their network's brain in 2. They put half the neurons on one GPU and the other half on a second GPU and trained them in parallel. And the really slick part was that they designed it so the 2 halves only had to communicate with each other at specific points. This clever setup let them train a model that was twice as big as anyone thought was possible on the hardware of the day. The third problem is the most subtle, but it's maybe the most important. It's called overfitting. You see, a network with 60 million parameters is so powerful, it has a dangerous tendency to cheat. It can just memorize the training images without actually learning the concept of, say, a leopard. It's like a student who crams for a test just by memorizing the answers. They'll ace the practice exam, but they'll bomb the real one because they didn't actually learn anything. The network had to generalize.
So their first solution to this was to never show the network the exact same picture twice. They used a technique called data augmentation. They'd take an image, extract a random patch of it, maybe flip it horizontally, or even just slightly change the colors and lighting. This created a practically infinite stream of new training data, and it forced the network to learn the essence of leopard, not just the specific pixels from the original photos.
The second part of the solution was a radical idea called dropout.
Imagine you're training a basketball team, but for every single practice drill, you randomly tell half the players to sit on the bench. The ones left on the court can't rely on any single star player being there. They all have to become stronger and more versatile on their own. That's exactly what dropout does. By randomly turning off neurons, it forces the remaining ones to learn robust features that are useful by themselves. So, with these 3 ingenious solutions ready to go, the fast neurons, the 2 GPU brain, and the powerful techniques to fight overfitting, the team was ready. They packaged it all into their model, which they called AlexNet, and they submitted it to the 2012 ImageNet competition. And here are the results. They're measured by something called top 5 error rate. That's just the percentage of times the right answer wasn't in the model's top 5 guesses. The second place entry, using all the best traditional methods, scored a 26.2% error rate, a very solid score. AlexNet came in at 15.3%. Now, let's be perfectly clear. This wasn't just a win. This was a demolition. Seeing it like this really puts it into perspective. This wasn't just the next small step. This was a fundamental leap forward. The gap between first and second place was just massive. Let me just put a single number on that. AlexNet's error rate was over 40% better than the next best competitor. In machine learning competitions, a margin like that is, well, it's basically unheard of. It sent a shockwave through the entire research community. But what does that performance actually look like? Forget the numbers for a second. The paper gives us some great examples. The network is shown this picture of a leopard in a tree. Its top guesses: leopard, jaguar, and cheetah. It didn't just get it right. Its wrong answers showed it actually understood the whole category of large spotted cats. And you know what? Even its mistakes were fascinating. It was shown this photo of cherries, and its top guess was Dalmatian. Now, why on earth would it say that? Well, it was focusing on the black spots of the container, a pattern it had associated with Dalmatians. So even when it was wrong, it was proving that it was learning visual relationships, not just memorizing photos. So, what was the aftermath of this stunning result? Well, this was about way more than winning a competition. This was one of those moments that fundamentally changes the direction of an entire field of science and technology. You can really think about AI history in 2 eras: before AlexNet and after AlexNet. Before 2012, progress was slow and steady. Then, in 2012, AlexNet provided the undeniable proof that this whole deep learning idea really worked, and that it worked spectacularly well at a huge scale. After that, the floodgates just opened. The world of AI research absolutely exploded, and the principles from this one paper became the foundation for the tech in everything from our phones to self-driving cars. The most crucial takeaway, the lesson that every researcher and company latched onto, was this: depth is the key. Making the networks deeper led to dramatically better results. The paper itself even says that removing just a single layer hurt the model's performance. And that became the new recipe for success in AI. Get your hands on huge data sets, build really deep networks, and unleash them with powerful computers. That has been the defining paradigm for the last decade. Which brings us to today. AlexNet, a true giant of its time, had 60 million parameters. Today's largest models have hundreds of billions, even over 1 trillion parameters. AlexNet learned to see a leopard in a tree. So the question this paper leaves us with is, what will a network that's thousands of times more powerful learn to see next?